Hello, everyone. My name is Umut Emek Demirbozan. I just obtained my PhD in IFAE in Barcelona. But I heavily collaborated with the University of Portsmouth. One of my co-supervisors is Shashadi Nadatur. That's where we apply the match filter technique for CMB lensing imprint of cosmic voids. First of all, thank you for accepting my talk for the organizers. Let me start by the outline of the talk. I'm going to give comprehensive background and developments in void science. Then I'm going to focus on modified gravity and the need to test lambda CDM. Then I'm going to refer to previous void CMB cross-correlation measurements, including ISW and CMB lensing. Then I'm briefly going to talk about the dark energy survey, which actually Juan Mena and some other speakers already talk about this fantastic survey. I'm going to introduce multiple void finders that apply to this photometric redshift data. And then I'm going to briefly talk about embodied simulation that we use, which is mice. Let's start. By the way, I have a bunch of slides, and there is more information as a backup slide. So if you download my slides, you will have more information about voids, since I don't have time to go through. But if you're interested, you're welcome to look at them. So why we test lambda CDM in this way? First of all, we know there are some anomalies. The best way to test lambda CDM, either you find discrepancies in the parameter estimates, mostly from early or late redshift universe. The main one is Hubble tension. But also, there are some anomalies that you observe, some specific object or some specific observation that challenge the model assumptions, such as isotropy, or general relativity. So some examples are CMB Cold Spot, lensing is low tension, or there is also a specific observation of L cluster. But also, while many people are focused on Hubble tension or some other parameter estimates tension, there were some excess signal coming from voids, especially integrated Sachs Wolfe effect. So I will briefly talk about that as well. So voids are these regions in the universe where there is not many galaxies, and dark matter density is very low. So a little bit of background. Voids are an excellent place to test modified gravity. So they dominate the universe, 60% of current universe volume based on voids. So there are many analyses. If you look at the literature right now, archive, you can see recently in the last 1 or 2 years there were many void papers, and there are constantly new techniques are announced. So, for example, fifth force, and many speakers talk about this, about modified gravity, FRN and DGP models predict different void densities than lambda CDM. You can have a look at this paper. And there are many papers about also void cross galaxy lensing, so cosmic shear. And also voids are ideal place to constrain neutrino mass, because the neutrino fraction is quite high in voids. And also modified gravity change the void number and size function. So there are different sizes of voids. So void function will significantly shift, and that can be also constrain modified gravity theories. And I'm going to briefly talk about the ISW effect that I mentioned. So ISW effect has been studied in DES, and there are conflicting claims in literature. So, and this is also related to CMB Cold Spot, by the way, because the hypothesis is that there's a huge void that might cause a CMB Cold Spot, but actually that's only possible if ISW signal is 5-7 times stronger than lambda CDM. And there is also recent results here coming from last 2 weeks, extremely low redshift that also claim ISW sign change, including high redshift ISW sign change coming from EBOS results. So this was interesting, and we wanted to probe the CMB lensing counterpart of this epoch. So basically, if you cross-correlate voids with the CMB lensing convergence map, which peaks around redshift 2. If you look at this one, the blue is CMB lensing channel, and the purple is where dark energy survey mostly probes. So we intersect in this region, and the future surveys will go deeper. So kernel peaks, for example, Euclid and Rubin LSST, and detection significance is much higher than ISW, because ISW is is a weak effect in lambda CDM, but we can go much higher significant. I will show in the final results. So let's talk about dark energy survey. So dark energy survey, Juan already talked about. So basically, it's an optical photometric ratio survey. It's 5,000 degrees square, mostly in the southern sky, because the survey is located in Chile. But the effective array is 4,200 degrees square, so the footprint is actually quite messy. So there are holes and irregular shape. I will show you. So and year 6 results are almost imminent. Maybe in a few weeks' time, or sometime they can be announced. So, but I'm using a special galaxy sample called Red Magic that has high bias and a high clustering from luminous red galaxies. So that makes it ideal to probe voids and define voids on them. So here you can see the footprint of the DES in red, and in blue is the Planck 2008 Kappa map. So it's the CMB lensing map. So there's a large overlap. And the green is DES year 1, and we also actually published another study on that DES year 1. Our signal to noise was not very high. But if you look at the shape, so this is the red, so quite irregular, and there are holes in it. So many void finders actually struggle. And that's why I'm going to refer to something called Voxel void finder that I use in my paper, in addition to something called 2D void finder. But the Voxel void finders are based on a code called Revolver. So it's purposefully designed for this kind of messy survey masks. So I'm going to talk about later. So let's introduce some cosmic void finders. So on the left, now you see a so-called 2D cosmic void finder. So that is defined in tomographic redshift bin. You basically have the tomographic redshift bins in your survey, and you project, and then you have a galaxy density map. So based on this galaxy density map, you identify each minima, and then you take a circular shell around, and you just increase this circular shell until the mean density within the shell reaches the mean density in that redshift bin that you projected before. So these are one way of defining voids, and in this way you have 2D voids. The numbers are less, much less than 3D counterparts. I will introduce in a minute. But you are sensitive to structures along the line of sight because you project it. So this has been used in many DES studies in addition to other surveys. So on the right, it's quite famous Zobov algorithm, zone-zone bordering. So this works with Voronoi tessellation. Basically, you define a space around the galaxy that is free of other galaxies. So you basically have a 3D tracer density. This is projected on the 2D, but imagine this in 3D. So every galaxy comes with a volume. So the larger the volume, the density is less. So we call this Bayesian. So we identify the minima, and this is called a watershed algorithm. Then you check the adjacent Voronoi cells. Cells should get smaller, and then that means the density is increasing. And then if density is getting lower again, the shells become larger. And we stop at that point, and we define this strange-shaped three-dimensional void. So we calculate something called effective radius. That's basically calculate whole volume of this Voronoi, some strangely-shaped 3D object, and then make it as a sphere. The volume should be equal to the sphere, and the radius of that sphere is the effective void radius. That's how we define. For voxel voids, we do something different. So we have all the three-dimensional data. We also have survey randoms. And what we do is the three-dimensional mesh interpolation. So basically, we have these cubes here on the right in the survey data. So and then you evaluate the density field on a mesh, and then you smooth by using a Gaussian filter. However, size of the mesh and the size of the Gaussian filter is a function of mean density. So we do not actually have any analysis choice when smoothing, and also when applying the when choosing the size of the mesh. So if there's high number density, so you take smaller cubes. If there is low number density, you take a little bit larger cubes and you smooth with a larger scale. So it looks like an ingenious algorithm. Then we identify local minima in this. And then after identifying local minima, just as in the Zobov algorithm, we stop. We use the watershed methods. And in this way, we will have some strange shape like three-dimensional cubes with adjacent cubes together. these are low density basins. So this way, in a Voxel way or Zobo way, you find much more voids because you do not do any basin merging as opposed to some previous studies. Some previous void finders proposed that we can do basin merging if you have like a 0.2 number density, not number density, mean density of the universe, and then you need to merge. So we do not do any basin merging, meaning that we find some voids that can be located on over density, which can actually give positive kappa imprint on the CMB because you are not exactly probed the large area. So also very important, there is this lambda parameter coming from revolver code for Voxel and also Zobo. This is the void effective radius, and this is the void density. So it's a function, 1.2, because in a paper, it has been shown to correlate with gravitational potential of the voids. So that means if you want to separate the voids, or if you're doing any gravitational analysis with voids, lambda is a good parameter to separate the voids and subgroup them. In fact, I'm referring to many studies right now, we use this lambda. So just to summarize quickly, on the left, 2D voids defined on tomographic redshift beams, and you have circular voids, and we find less of these voids used in many DES studies, year 1 and year 3. And on the revolver, we have Zobo-based and also the cubic voxel that I mentioned, which gives you lambda output. So in my study, we use these voxel voids in addition to 2D voids, and I'm gonna now focus on the details of my study. So before that, let me explain my simulation that we use to calibrate our filtering and have the lambda CDM expectation. This has been also used in many DES studies. So it is from Barcelona people in ICE. So, and some speakers already mentioned my simulation quite a lot. It has a CMB lensing kappa map, and it just generates, so we use up to actually ratio 0.8 here, but yeah. So it offers some finer mass resolution than other simulates, and we make sure the HOD parameters are right. So we are simulating what we observe in DES, photometric redshift data. So we have the red magic counterparts of galaxies. So we use this mock to create the templates that are lambda CDM expectations. And how do we do that? We basically use a stacking method. Sometimes it's called poor man's method. So if you look at here, this is bin 1, and this was the lambda parameter that I was referring before. So this lambda, in this bin, you usually find voids that are larger and imprint significant negative kappa, so because the blue is kappa, so basically this is the largest one. So this is, sorry, I need to, all right. So this B1, the B, is actually this blue one here. And then if you look at the B5, you look at here, there's a hot ring, because these are smaller voids. These are on top of the over density. So this is this one here on top of there. And so forth and so forth. Like the beam 4 is there is also smaller hot ring, and it is this orange one. So this is what lambda does. So it basically groups the voids because of gravitational potential, and their imprint on CMB lensing is different. Of course, this is stacked. So we went to void positions in CMB lensing convergence map, and then we stacked them together. You cannot see the imprint of one void. So this is from Raghunathan et al. This introduced the match filtering method and this lambda-based separation. So we use heel pi, and this is what we do in simulation, basically stacking. So there are two main methods when you're doing these studies. And so one is the rescaling, and this has been used in ISW studies. On the right is the match filter. So also when you do this, you can do the void radius. You can rescale the void radius, or you may not rescale the void radius, you're stuck. So let's talk about that. So the match filter maximizes signal to noise. In layman terms, you basically look for the signal that you expect. You calibrate it from simulation. So there is no arbitrary smoothing scale. We do not use any Gaussian scale. And it uniquely determines spherical harmonics based on the function that you're expecting, your template you're expecting. And it encapsulates all the signal into the void center. So that means it's also a cheap algorithm computationally. You just need to stack void centers finally after filtering for each void bin. you have a match filter Planck CMB lensing map, then you go to the corresponding voids in this data, and then you stack the centers. So this encapsulates all the signal into void center. It's very important because I will show the results. So this on the left is the match filter. The template profile, we measure on theta, we don't rescale it, and these are the corresponding spherical harmonic coefficients after applying the match filter. So here, maybe I can show more. I mean, if this profile would different, because we separate the void center signal and the normalized shape function fit into the template, from the shape function, we get the spherical harmonic coefficients. That is our filter to filter the CMB lensing map. So we make sure we have 3 redshift beams, and each redshift beam is the 3 lambda beam. And then we have 9 beams of voxel voids that I explained before. Here, 2D voids. Since 2D voids are projected, they are not 3-dimensional. I just use the density. So once we agree, mice and des voids are like void function and everything is agree, we get the results. So these are void templates here that I showed you before. So 3 redshift beams, and each color represents different lambda beam within each redshift beam. So we have 9 beams. So these are our expectations, mice lambda beams. And based on these templates, y-axis is kappa in unit of 1000, and theta is the degree in sky. There is no rescaling. And once we have this, based on this, we define match filters. So for the corresponding ones. And this means the match filters ready for each void beam. And what we do is they obtain the results. So on the y-axis, the Des tree. On the x-axis is the mice. So these are the 9 beams for voxel. And here on the right is the 2D voids. So we get 5.92 sigma and 4.6 sigma from voxel voids. And this is a very good agreement with lambda CDM. And then what we do is also 2D superclusters, meaning that I invert the void finder in the galaxy density map by multiplying -1. And then what I find is a good agreement again from 2D superclusters 5.94 sigma. On top of that, I use a different method that I showed you before, Gaussian filtering. So there, I do not stack the void centers. This blue is the mice signal for voids, and also this here 3 signals. So you can see the good agreement. This is rescaled to void radius here on the x-axis. On the y-axis is the kappa, and I do the same for superclusters. So here I got 6.3 sigma detection, and for the supercluster 7.1 sigma detection. So the key conclusion is that we have investigated CMB lensing imprints with voxel. The first time in the literature, we used 2 different techniques, match filter and Gaussian filtering technique, and we agree with lambda CDM very well. Look at the final results here. So these are, each color is a different study. My paper is on the brown bar here, down here. And this was an earlier study by DS, the green, that indicated moderate tension, because this didn't use the updated red magic algorithm, which affect your void function and void numbers and sizes. But if you look at all the other studies from Wolfe, and I will have your particular attention to this purple one, Observatory, which uses Desi legacy, much higher footprint, and also much deeper redshift range. So it goes, it also agrees with quite constraining 1.2. This is like 15 sigma detection. So the current literature highest is from that. So basically, I updated the previous DES results, and it is now in agreement with lambda CDM, and it is also confirmed by other survey, CMB lensing of voids. So basically that's it, and thank you so much for attention.
Thank you so much. And questions?
Hey, thanks. That was really interesting. I'm wondering if there's any sensitivity to your derivation of the matched filter because mice has a single cosmology that you are then assuming when you run the matched filtering calculation.
Yes, that's a really good point that we have considered a lot before. And actually, your question is relevant to also our detection significance, if I can go back. This is the other method, the Gaussian filter, and you see here the detection significance in the same data set higher than match filter. And this is a caveat of using only one realization. Normally, the other paper I show you, the first profiles, they use 180 realization of Takahashi simulation. And I think future studies could be in that way. But this also can have give you constraining power. But in general, you are right. It's much better to use multiple realizations in this kind of studies.
There is one more here.
Yeah, all right, thank you so much for a very nice talk. I was wondering, how does the uncertainty on the photometric redshift estimation affect your void finding algorithm?
Yeah, I think that affects Voxel a little bit more, but let me become. Yeah, so in Voxel, we smooth the 3D density field. So basically, this is, we also use the survey randoms to have the density field. Basically, we do not find really small structures, so we are more sensitive to the statistical. It shouldn't affect the main statistical power of Voxel voids, but it affects. In the other algorithm, 2D, you project, and when you're projecting, defining the redshift thicknesses, you do at least 2 times larger than the photometric redshift uncertainties. But then actually, this is why I use red magic, because they have the lower photometric redshift uncertainties. And if you have a spectroscopic redshift survey, that could have been much better. But for this case, and many photometric redshift case, using Voxel and maybe dual methodology using 2 different void finders, which will have slightly different sensitivity to photometric redshift errors, can be a good idea.
Thank you very much.
Thanks.